Good morning, students. Welcome back to the class of what do you call system software. Previous class, we just discussed about the machine-dependent assembler features. We shall go a quick review on this, and we can continue. Actually, the machine-dependent assembler features deals with the various formats of instructions in SIC and how they could be assembled. Right? Format 1, as it doesn't contain any operands, we don't have any, only the opcode will be there. And format 2 contains registers, register to register operations, which will be represented by using 4 bits. Each register is represented using 4 bits. And the format 3 has got format PC relative addressing. We have just seen how to assemble them by making the flags and grouping 4 bits together and computing the object code. So this we have discussed in the previous class. And similarly, we have seen some more examples of PC relative as well as base relative addressing mode also we have seen, which is represented between base and no base. And here also the B bit will be 1, P bit will be 0, and E bit will be 0. And we group 4 bits together so as to compute the object code. And the important thing is opcode is of 6 bits. So, but we need 8 bits to represent the opcode. And am I audible again? Because there is a power problem. Please do respond in chat. Please do respond in the chat if I am audible. Please do respond in the chat if I am audible. Okay, we shall continue. Fine. Okay, base relative also we have just seen how to assemble it. Similar way we should compute the object code by grouping 4 bits. So these are all examples we have seen, and also we have seen a program for program example of how to assemble the SIC program. Important thing is how to differentiate between SIC and SIC program is that we'll be having the immediate addressing mode as well as format 4 addressing mode, which will be not be there in the SIC programs, right? And immediate addressing also some examples we have seen, and here also the same way we group the 4 bits so as to compute the object code. Okay, and this format 4 direct addressing, which will be usually represented with a plus in front of the instruction, and it can also be used as an immediate addressing, or you can use an operand in place of your what we call format 4 instruction. This much we have seen, and also we have seen a program which copies the 10 bytes or reads the 10 bytes from the input device and then stores it in a string. We have seen this example, and I also requested you people to work with much more examples. Please refer the textbook, and you can download a copy of textbook also, and can, if you don't have the textbook, you can also see some more examples of the programs, how it could be assembled. So a few variations also you can see, and we can have a separate discussion session on those programs which is having bit variations. Okay. We shall also see some more variations later. Fine. Okay. In pass 1, the addresses will be assigned, and usually we go for relative assembling, wherein we'll start the addressing from 0. In the pass 1, we'll be means we're going to assign the address starting from 000, right? And depending on the length of the instruction, the addresses will be allocated. If it is a format 1 instruction, only 1 byte will be allocated. If it is format 2, 2 bytes will be allocated, right? And if it is format 3, which will be allocating the 3 bytes for the instruction. So the location counter will be incremented by 3 for format 3 instruction. Okay, like in row 1, 2, row 2, 3, 4, 5, 6, 7, all these things we are doing the same. But in row 8, it is a register to register addressing mode, so it is a format 2 instruction. So wherein we are allocating only 2 bytes per byte. So this what is done in pass 1, and all the declarations will be allocated size or the addresses based on the size of the variable or the constant. Input device is a hexadecimal character constant whose value is F5, and str1 is a string of 10 bytes, right? And in pass 2, we assembled each of the instruction based on the type. Majority of the SIC program instructions are format 3, and majority of format 3 instructions, until unless it is not specified, is a PC relative addressing mode. Based on this, we have assembled. And even the immediate addressing mode is also been seen like this way. Okay, so this and all we have seen in the previous class. It's just a quick walkthrough through this particular. So today's discussion will complete the machine dependent assembler features, and then we move on to machine independent assembler features. That's what is the actual task for the day. So quickly we go to the last part of the program, wherein we have assembled each of the instructions and we have written the object code in the file. Means we have written the object code beside each of the instructions. This much we have done. And in our program, specifically in this example program, we don't have format 4 instructions, so that's not there. Okay, but there is an issue. One thing is that now we have used the relative addressing 0000 for assembling all the instructions. If it is a format 2 instruction, we don't have any problem. If it is a format 2 instruction, we have both the operands in the register, so there will be absolutely no problem. So the register numbers remain same. So whether it is assembled relatively or if it is assembled absolutely, it doesn't create any problem. But if at all we do have format 3 instruction, then also beside the instruction we are just mentioning the offset or the displacement. So which is changing? Relative. So why I am telling you this is that, so for example, we have assembled this program starting from the address. We request after assembling, we give this object code to the loaders and linkers, whose task, the loader's task, is to ask the operating system for an address where to load this particular program. If the operating system provides some address, let me say 3000, then with instruction which is assembled using 0000 will be placed in 3000, correct? So next 0003 will be placed at 3003. This doesn't affect format 2 instruction, not a format 3 instruction, because format 3 instruction contains displacement. Something like in a classroom, I have some 50 students sitting in the benches. I'll tell, move to the next classroom exactly in the same order how you are sitting in this particular classroom. Then what happens? The first bench, first person should be moved to the first bench, first person of the next room. Only the room number changes. The placement of the students within the classroom will not change. So that's the reason format 3 instruction also will not be affected at all, because we have at the 003 we have an instruction. For example, here at row 5, I am telling JEQ in loop. In loop is at exactly previous instruction. So I should go back to from 0009, I should go back to 0006. Means to say 9 minus 3 should happen, correct? So if it is at 3000, if the addresses are assigned from 3009 to 3006, I am supposed to jump. The difference will remain 3 only. Same way, in the row number 9, JLT in loop is there, wherein we are supposed to jump from 0014 to 0006. Then also, the displacement will going to remain the same. That is 14 minus C. Whatever is the displacement we are going to get, that will remain the same, right? If it is placed at 2000 also, the displacement remains the same. If it is placed at 5300 also, the displacement remains the same. So means to say the conclusion is that format 1 instruction is not affected because of relative assembly. Format 2 instructions are also not affected because of relative assembly. Format 3 instructions are also not affected because of because of relative assembly. then who will going to have the problem? If at all I have a format 4 instruction, in format 4 instruction I have specified the address as something like 0017. Now the operating system has given you the address 3000. So the address should not be 0017, but instead it should be 3017. That should be changed. So the operand address in the format 4 instruction is supposed to be changed whenever we are going for a relative address. That concept itself we call it as program reallocation. Very important concept, usually asked many times in the machine independent assembler features. Program reallocation. What the program reallocation specifies is, if absolute addressing is used for assembly, the program can only be loaded in that specific address, which is actually impractical. So for that reason, we usually go for what? Relative addressing, right? Desirable is the program that can be loaded into any memory location that is available. So we are going for relative assembly, right? Okay, for a second. Okay, we usually go for relative addressing, means that every first instruction of the program is going to be assembled by using 0000. Fine. Okay. And then, relatively all other instructions are assigned addresses starting from 0003, 06. So after the OS receives the load address, hello, please write in the chat box. Okay, let's continue. Fine. Actually, there is a power problem, so that's why this is happening. Fine, anyway, we'll continue with from where we were. Okay. Okay. Yeah. So where we were is program reallocation. Okay. See, there is a table gives you an example of how exactly the reallocation will be there. For example, LDX #0, which is an immediate address. We assembled it using 000, considering the address. But now it is going to become 3000. Similarly, we have the address at LDS at 0003, which will be changed to 300. Similarly, but these and all are immediate addressings. As anyway, we don't have any issues with them. But the issue actually happens with format 4. If it is a format 4 instruction, then this is an issue. What is the problem? Just have a look at it. At 0030, we have an instruction, add alpha. The add alpha is a format 4 instruction. You can see a plus mark in front of the instruction. It is a format 4 instruction. Means the complete address of 20 bits will be specified for alpha. But alpha is at the location 0056, which is a relative location, not the absolute address, which is a relative location, 0056, wherein alpha is declared as an integer variable. When we assemble it, we're going to get something like this. Add is a 1H output. So 10001 and 10 is written in the 6 bits. And N and I bits are 1 and 1, X is 0 because it's not indexed, and B is 0, P is 0 because it's a extended format 4 instructions. It's not a what you call format 3 instruction. Fine. So, and the address 0056 is as usual represented in the 20 bits. That is first 4 zeros, next 4 zeros, and next 4 bits is representing 50101, and next 4 bits is representing 60110. Now we're going to get the opcode when we combine 4 bits. 1B, that is 1011 gives you B, and next 0001 gives you 1. And then next 4-bit zeros gives you a 0, next 4-bit zeros gives you a 0, and next 0101 gives you a 5, and 0110 gives you a 6. Actually, the address is 0056 relative, not absolute. Now we are going to give this object code to your home loader. The loader asks the operating system to give the load address. The operating system gave the address 3000. For example, let me believe that the operating system has given the load address as 3000. So this value, the direct address 20 bits, should not be 0056, but it should be 3056. So this change need to be made for the operand address in my program. Who should do that? Now, anyway, assembler completed its task and gave the object code. So now the loader should do this particular task. Now the question is that how come the loader knows which instruction need to be changed and which byte of this instruction is supposed to be changed? I don't need to change anything in the object code of add alpha till the opcode and the flag bits. Only thing is that 20 bits of address what we have, that is supposed to be changed. Only 20 bits of address is supposed to be changed. So it's a responsibility of your assembler to inform the loader that the alpha is been assembled relatively, but its address is supposed to be changed depending on the load address, whatever you are getting it from the operating system. So it's a responsibility of the assembler to indicate something that informs your loader to change the relative address to the absolute address depending on the load address of your what is being given by the operating system. This information has to be communicated to the loader. So we use one separate record along with the text record, header record, text record, and end record. We use an additional one more record in our object code file format. That's what we call it as modification record. And what modification record contains? The column 1 of your modification contains M, indicating that it is a modification record. Next is column 2 to 7 is containing starting address of the location that has to be modified. Now the starting address of the location means that place exactly where your operand address starts, not the instruction starts. Means in this 6 and 6 bits we have opcode and flags. We should exclude the 6 and 6 bits, and we are supposed to start from the place where the direct address of 20 bits is starting. That's supposed to be the kept in mind, that the starting address of the location means not the instruction, but it is from the place where the operand address is starting. Okay, and column 8 till 9, there is one column. The only one column we have, we don't have more than that. Please observe that 2 to 7 we have 5 columns or 5 bytes we have, but in 8 to 9 we have only one column which should specify the length of the field or the size of the field. But using one field, I cannot specify the 20 bits. Please understand, I cannot specify the 20 bits. That means your total size of your operand cannot be specified. For that reason, it is specified using half byte. That means nibbles. Means we can specify only one byte. Within one byte, I need to specify the size. For that reason, half bits will going to be used. See the example, you can understand. Now, modification record M 0056, which is the relative address. How many bits is supposed to be changed? 05 bits is supposed to be changed. What do you mean by 05? We have 5 into 4 will going to give you 20 bits. So we are specifying it in a half byte. 5 4s are 20. So 20 bits, if you divide it by 4, nibble is 4 bits. Half byte is 4 bits. So 20 divided by 4, you are getting 5 bits. So next consecutive 5 bits is supposed to be changed. Means the entire operand address is supposed to be changed. Or else you can remember the modification record. easily like this way, that it will happen only with format 4 instruction, and format 4 instruction obviously will have 20-bit operand address that is specified in half byte. So the last column of your modification record will always be 05. You can write 05 or you can just write 5. Both are valid. In some examples in your textbook, M, the starting address, means the operand address, 0056 as in our example, comma 5 will be there. There will be a plus. There will be a plus, or there can be a minus also. There will be a plus or minus, plus the starting address of the program. That means the load address, whatever is given. So if at all I need to write like that way, I should write M modification record 0056. That is the address of your operand. 5, that 5 bits, 5 half bits need to be changed. And then the next 20 bits need to be changed. Plus, I should write load address. Load address is what? As we have assumed, it is 3000. Load address is 3000. So like this way, we can specify. These additional records are specified along with the header record, text record, and end record as an indication to your loader. Information is conveyed from assembler that how the program need to be modified. So this ends your machine dependent assembler features. Now we shall move on to the next one more concept, machine independent assembler feature. Okay, yeah, machine independent assembler features. Here our intention is to learn these things. There are some machine independent assembler features which is not only specific to SIC and SIC. It can be commonly be present in different machine architectures also. Such sort of features we call it as machine independent assembler features. And more or less these machine independent assembler features are additional facilities provided by your SIC or whatever the machine is. So additional facilities we're going to list in this particular. But anyway, we are still using SIC and SIC-XE as our what you call reference machines. There is absolutely no change in that. And we're going to derive the examples based on that. So what are the machine independent assembler features? Are literals, symbol defining statements, expressions, and also we have something called control sections. We're going to look at those particular program blocks and control sections. These 4 will going to be what you call machine independent assembly features. So either of any one of them may be asked in your examination. So once we have completed this, we have completed the assembler SIC, SIC-XE architecture. Next part will going to be a small concept about your macro processor. If we complete that, module 1 will going to be completed. Then we go on to module 2, which is a loaders and linkers. So only this much. We're going to talk about a machine architecture, then an assemblers, and then macro processors, then the loaders and linkers. This is the only concept of your what do you call system software. Rest all anyway we are doing compiler design. So we'll continue with those particular things. Fine. Okay, literals is the first machine independent assembler features. If the program wants to use the value, character value as a constant, character constant, as part of the instruction without declaring it. Remember that. That can be done without declaration by using something called literals. And it's a very simple way we can use it. So this is what is the way we can use it. A literal is defined with the prefix equal to. And please remember, these are only for character and string constants. The numerical constants, that is your integer or floating point, will not apply for this, because for them we have immediate addressing. That too, specifically for integers we have immediate addressing. We don't have any mechanism of what do you call floating point arithmetic. So not being discussed in SIC-XE also. So that's anyway feature is not available. Fine, no issues. As I again clearly mentioned you, SIC and SIC-XE is a hypothetical machine, not a real one. Fine. Okay. The literal is defined by using this equal to sign beside the instruction, equal to followed by the specification of the character value or a string value. Either of them you can use. Okay. So see an example. Test device, in device. We'll going to see with literal and without literal how the difference happens. We have test device, in device, jump equal to in loop. This pattern we have used many times. And if it is not equal to, then we're going to be reading the input device. And for that, in device is uniquely identified by the hexadecimal constant F5, which is been declared somewhere later. Yes or no? You can see that there is a declaration of input device with the value F5. Okay. But the same thing, if at all we write it using literals, is as simple as that. Test device, we are not declaring the in device, input device as a character, hexadecimal character constant, but instead we are using ID is equal to XF5, which is indicating the value F5 need to be tested. That means the device ID is given directly as a hexadecimal constant in the instruction itself. The same is happening in the third instruction also. So RD is equal to XF5, which we are specifying that directly the value itself is used. This is one way of using the character and string constants. There is one more example you can see. We have an instruction LDCH, load character to accumulate a string 1 comma X, and string 1 is declared somewhere there in str1 as a byte, which is a character whose value is NEW, right? Which can be, instead of this, written directly like this way using LDA instruction. Directly, the accumulator will be loaded with this entire string NEW directly by using LDA instruction using it. LDA is equal to C. So it is suitable for a character constant or a string constant. So you are supposed to, character constant and string constant. The character can be an ASCII or it can be an hexadecimal. So for that reason, either specifying the X or either specifying a C is mandatory. Fine. Okay. So warning of time up. Fine. The next concept we do have is LTORG, which is a small concept. Only two things I need to specify. LTORG is an assembler directive. LTORG is an assembler directive. If you can write this anywhere in your program. What is the use of it? Yeah. The use is this, that we have used X is equal to XF5 and C new, all these things. Where the memory should be allocated. If it was declared, your location counter should have given an address for it, and the memory is allocated in that address. But now we are using the value directly, somewhere it should be stored. So for that reason, LTORG is an assembler directive which creates a literal pool. A literal pool is the place, means some address space wherein your directly used literals are given the addresses. And the LTORG, where it appears in your program, that the place your addresses for literals will going to be given. You can, that's why I told, it's your choice, wherever you want, you can call the assembler directive, and nothing before, nothing after your LTORG. So you are just telling LTORG. So it will give the address space at that place. So what you can do is, you can use the literals in your program. At the end of the program, before the declaration or even after the declaration, you can call the assembler directive LTORG. So the address for all your literals will going to be allocated at that particular place. Right? This is about the literals. What we are going to see next is a symbol defining statements. In the next class, we are going to see that. So thank you for joining. Anyway, due to the power problem, some disturbance happened. Anyway, I'll upload the video also. So by combining both the things, so that's how we're going to do that. Fine. Thank you.